Lab 2, motion of a falling object. We begin again with Newton's second law. For a falling object, the object starts at rest and gains speed as it falls before hitting the ground. The first model will include only the effect of gravity. The second model will include the effect of gravity and the effect of drag. As a refresher, Newton's second law, or the momentum principle, says that the change in momentum is equal to the net forces on a system, which is the total pushes and pull on the system multiplied by the change in time. From algebraic manipulation, we can determine that the change in velocity over time is equal to the net forces on the system over the mass. After uploading the video into Tracker, I set the coordinate axis with the positive y-axis pointing to the left, which in reality is up, so that the fedora will fall in the negative y direction. I measured the height of the hat to be 13 centimeters, or 0.13 meters, for the calibration stick. Next, I set the video in motion within Tracker and captured the point of mass to get my experimental data to use in my analysis of the computer models. To configure for Model 1, I first used find and replace to replace the term ball with fedora. I then entered the weight of the fedora, which was 135 grams, or 0.135 kilograms, into the variable fedora.m. As for the initial position, I changed the y-coordinate of the vector to 0.784, which according to Tracker was the height of the object when I dropped it. I changed delta t to 0.033 seconds, as that is the change in time that is used in Tracker. Otherwise, I did not change any of the variables. I also changed the while loop to end at 0.733 seconds, as it does in my experiment. In addition, we were told in our assignment that the magnitude of the drag force is proportional to the square of the object's velocity. Since we cannot multiply two vectors together, since we are calculating the magnitude, we can multiply the velocity vector by its magnitude to get the same value. Therefore, the drag force is equal to negative b, which is the proportionality constant, times the velocity of the fedora, times the magnitude of the velocity of the fedora. Additionally, I changed the arrow scale to 1.512 based on the information told to us in the lecture video. Since I want the arrow to be 2 meters in the module, like it was in the lecture, I set the arrow scale to be the length of the arrow over the magnitude of the weight, which is equal to 2 over 0.135 times 9.8, or 1.512. Now if I run the module, I see the yellow arrow as the ball falls, and the graph has a very similar curve to my experiment, so I assume that this is decent data. I will take the data from the spreadsheet that is produced and put it into my Google document. Since I've already changed the formula for the drag force to be negative b times fedora.vel times the magnitude of that velocity based on the information given to us in the lab assignment, I just need to figure out b, the proportionality constant, for this model. This will be done through trial and error so that the experiment will end at the exact same point as it does in my experiment. My experiment ends at negative 0.494 meters, though through trial and error I determined that b is equal to 0.337. If I now run this module, I now see a slight blue arrow that is off the screen that is representing the drag, and a model that is also similar to what I have in the experiment. So I will also take this data and put it into Google Docs. After plugging in all the data for both of my models and my experiment into Google Docs, I'm able to see the correlation between the three models. The blue line represents my experiment. So the hat takes a while to fall at first and then slowly dips down. The red is where gravity is the only force, so the hat would fall faster without any drag and would fall to a different height in the same amount of time. And the yellow line is with the b coefficient that I set so that the hat would land around the same position based on the drag force as it did with the blue line. The yellow line is much straighter and doesn't completely follow the blue line, but is a much closer fit to the experimental data than the red line of the force only by gravity. Terminal velocity would be the maximum velocity that the object would fall, so it would be that the object has hit constant velocity. In both the blue, the yellow, and the red models, it appears like the graph becomes linear. The blue only bumps when the hat hits the ground, but imagine that the object was initially thrown downward I believe the terminal velocity would be the same. To justify this belief, I changed the velocity vector for the initial condition to 0, -5, 0, so that the y-coordinate would be throwing the ball straight down. In my new model, the green line now represents the ball being thrown down, with the b constant being the same as it was in the yellow model. Looking at the yellow and the green lines, though the speed of the ball going down seems faster at first, they both seem to be running parallel, which would mean that the change in position over time, or the velocity vector, would be the same. Therefore, terminal velocity would be the same whether the ball is thrown or if it's just dropped.